So this would have been the very last question in 2022, question 10, paper 2, and it really would have challenged a lot of students. There's a lot in this question, and I'd say the biggest challenge initially would be identifying how you approach each question. Now, a well-prepared student will look at part A, and straight away they'll spot that it's a Z-score question, right? And then they look at part B, and it should be jumping out of them that part B and C are both Bernoulli trials. Now D then and E would be quite difficult really to identify how you would approach it, right? So once we read through part D, you might realize it's a combinations question. Now there's two ways of actually doing this question, and interestingly then with part E, once we read through it later on, you'll see that it's actually a Z-scores question as well, right? So Z-scores, Bernoulli trials, and then back to Z-scores again. So if we look at part A, and now as I mentioned earlier, as soon as you see this question, like by the time the leaving cert comes, as soon as you see this question, you will know that it's a Z-scores question. Right, so find the percentage of runners of the heats that took more than 240 seconds. So Z-score formula should be coming into your head straight away. And when you're doing these, you should always start off with a diagram. Right, so they mention here that the mean is 225. So it's normal distribution, and we want to know what the percentage of runners that would take more than 240 seconds. So it's good to indicate that in the diagram, what exactly we're looking for. What is that percentile there? Right, and once you have that, the usual steps are just list out the data that you have. So the mean is 225, standard deviation is 12, and the piece of data we're investigating is 240. If we convert that into a Z-score, it comes out as 1.25. And this is where your percentiles come in then. So if you convert 1.25 to a percentile, it's 0.8944 from your log tables. But from the diagram, we can clearly see that we want what's greater than 240. So it must be, in this case, 1 minus 0.8944. Okay, and at this stage, when you get to the actual leaving cert, that calculation there shouldn't be a problem for anybody. You should be able to spot straight away that it's not the number directly from the log tables that you're taking. That refers to this bit. It's 1 minus that number. And it's always either that number or 1 minus that number. That's what you're looking for. So your answer is 10.56. Now, as you can see, the marking scheme here, that was 10 marks there for that part A, part 1, which is significant enough there for such a relatively straightforward question. Now, part 2 then, and this often happens, right? Part 2 is another Z-scores question, but what they're doing is they're working from in the opposite direction. Okay, so here we were looking for the percentile. Here they gave you the percentile. Okay, so we're using the exact same diagram, right? But we're working backwards to get this score here. What time would encapsulate 20% of the fastest runners? Okay, now a common mistake here, I would imagine, is to assume that fast means the right-hand side of the graph, but the 20% of the fastest runners would actually be the lowest times. Okay, so just be careful with that. So it's around here that we're looking for, and you can see now what I mean by, if you have the graph in front of you like that, it gives you an idea for the score that we're looking for. So it's about 210. If you're getting a result at around 210, 215, that's a good sign. So the key to this type of question is you do it in the exact same format, right? So when it was part 1, right, we found our piece of data, we listed out our piece of data, we found our Z-score, and then we went on to find our percentile. And do the exact same thing here, right? So list out your data, which is the exact same, except this time we don't know the time that we're looking for, right? That's what we're actually looking for overall. Now you fill out your Z-score exactly in the exact same way, but obviously we can't find that Z-score because we don't have X, and then you work with your percentile. Okay, now in this case, this red section here is 20%, right, or 0.2. Okay, but if you know your Z-scores and your percentiles well, you'll know that in the log tables, it doesn't go less than 0.5, so it's actually 0.8. That's the Z-score we're looking for. The Z-score that corresponds to 0.8 of the data, right? So that's the key thing. Now, the second thing is that it's a minus Z-score. That's the extra complication in this, right? So if we put all of that then together, if we look for what 0.8 is in the log tables, it comes out as a Z-score of 0.84. Because we can clearly see from the diagram that it's less than the mean, that means that Z-score is going to be a minus. Right, so there's a lot in there. Okay, so if you're not very familiar with your z-scores, if you're not fully up to date in the z-scores, there's absolutely no point in worrying about this question. Like, you need to know this process inside out, and if you know this process inside out, then all of this will make sense. Why is it 0.8? Why is it a negative z-score? Where did I get 0.84? But once I have my minus 0.84 then as my z-score, I can use it to solve this problem here. Right, so solve this equation. Simple linear equation then to solve, and we end up at 214.92, which actually should be round off to 215 seconds, and that looks about right there. Okay, 215 seconds. So that basically means that if they get 215 seconds, they're in the top 20% of the runners. And if you look at the marking scheme, even though part 1 was a lot easier, that was worth 10 marks, whereas part 2 was only worth 5 marks, right? So even though it's a much more challenging question, it was only worth 5 marks. Now, part B then, right, completely new part of the question, relates back to running, but this is a Bernoulli trials question. Right? Sally takes part in a number of different races in competition. She has a 5% chance of making a false start. What's the probability that this happens in the 4th race? So when you're doing this, you just list out your event. So race 1, it's not false. Race 2, it's not false. Race 3, it's not false. And in race 4, the false happens. So if it's a 0.05% chance of it being false, then it must be 0.95% of it not false, is the best way to phrase that. So the probability of this happens is 0.95 by 0.95 by 0.95 by 0.05, which is this simple way of writing it there. Okay, and it's good to write it out like this, because when we get, now again, this is a 5-mark question, but when we get to part C then, this is a proper Bernoulli trials question, where you need to use the Bernoulli trials formula. So 20 relay teams take part in the competition. For any team, the probability that they drop is 0.1. Find the probability that at most 2 teams drop the baton during the competition. Okay, so there's quite a lot in this now, right? And when you, again, a well-prepared student, when they see the at most phrase here, that should be ringing a few alarm bells. And what you need to do is kind of translate that now into something that makes sense in terms of Bernoulli trials. So first of all, how do you spot that it's a Bernoulli trials question? How do you know that we need to use this formula? And there's no easy answer to that. You just need to be familiar with it. You need to be familiar with these type of questions to know that this must be something to do with Bernoulli trials. Now, at most 2 teams, that translates to that, first of all, either exactly two teams drop it, or else exactly 1 team drops it, or else no teams drop it. Okay, so you must take each of these 3 things then individually. Okay, so how do we find the probability that exactly 2 teams drop the baton? Well, that's your n is 20, your success, in this case dropping it as a success, is 2. Your probability of success is 0.1, your probability of failure is 0.9. Sub it into your Bernoulli trials formula, and that's the probability of exactly 2 teams dropping it. Right? Then you do the exact same thing with 1 team. Probability of 1 team dropping it is this, right? And when we sub it into the formula, we get this. And in fact, you didn't need to really do the Bernoulli trials formula here, but it's good to see how it works. And then the probability that no team drop it is straightforward enough. It's just 0.9 to the power 20. Okay, so that's that. So what's the probability of this or this or this happening? So to get at most 2 teams, you just add up all of those probabilities, which gets that. Now, if you look at the marking scheme for that, as you'd expect, it's 10 marks because there's a lot of work in there. But you can see that the partial credits there are quite generous there. If you do any work of merit here, even by identifying that it's Bernoulli trials, you're getting a nice bit of marks there. Now, there's a lot to unpack now in this particular question, right? It's definitely not immediately obvious how you solve this, okay? Now, if you read through it, right, 300 runners running in the race, they're numbered from 1 to 300, no 2 runners of the same number. And this is the key line here, the second last line here, work out the probability. So 2 runners are picked to random. What's the probability that it adds up to 101? Now, as you see, there's 2 methods to doing it. Now, one is quite straightforward once you see it here, but it would have been very difficult to spot this. Okay, but we want to know what the probability that they add up to 101. So how many possible combinations would add up to 101? Right now, if you actually list them all out, you will see that that mightn't be a bad old way to do it, right? So what are the possible successful outcomes here? So there's obviously 1 plus 100. If 2 of them were picked, that adds up to 101. 2 plus 99. Now, if you keep going with this pattern, right, all the way to the very end, 48 plus 53 will give you 101. 49 plus 52 will give you 101. 50 plus 51. And once you've got to this, then you're kind of back to square one again. So these are the possible combinations that will add up to 101. Now, how many of them actually are there? Well, there's 50 of them. So there's 50 possible successful outcomes here, right? Now, how many actual outcomes are there in total then? So how many different combinations of 2 runners can you have? Now, if you're very familiar with combinations, you'll spot that it's the combinations formula we're using here. So we're choosing 2 from 300. So it's just simply 300C2. Okay, now a lot of students have big issues with combinations, and spotting that this is a combination and being certain that it's a combination is quite a difficult thing to do. So don't worry too much if that looks a bit intimidating. How do they get 300C2? So you can either see that or you don't, and when you get very familiar with combinations, that will kind of make sense. And if you went back over combinations now, that would make sense. But that is quite tricky. So there's 50 successful outcomes. There's 44,850 outcomes in total. So your probability is that. Okay, that breaks down to 1 over 897. Okay, and the good news, it's only a 5-mark question. Okay, now there is another method of doing it then. Now, if you think back to first year maths or junior cycle probability, like as I said earlier, this question might look kind of familiar, where you had like 2 dice and you were rolling 2 dice and you were adding up the result or adding up the outcomes. And in those questions back in junior cert, you would have used a 2-way table. Okay, so it's actually possible to do that here as well. Now, the problem is there's 300 different numbers. Okay, so you're not going to do a 2-way table of 1 to 300. Okay, so when that happens, when big numbers like this happen, sometimes a nice technique is to just imagine that instead of 1 to 300, it was a more manageable number. What if there was only 10 people in the race? Okay, so if the question was numbers 1 to 10 inclusive, with no 2 numbers of the same number, this is your 2-way table, what it would look like. Okay, and then you'd fill in the 2-way table like that. So like 1 plus 2 would be 3, 1 plus 3 would be 4. This is what the sum of the numbers would be. You can fill all of those in, and you'll notice that there's 1 row missing, or there's 1 cell missing in each row, and that's where the numbers are the same, because there are no 2 numbers the same. Now, imagine that the question was, so sorry, before I go into that, how many outcomes are there in total? There's the 100 outcomes minus the 10 outcomes that where the numbers are the same. So there's 90 outcomes in total, right? So if the question was find the probability that it adds up to 9, okay, well look, there's 1, 2, 3, 4, 5, 6, 7, 8, so that's 8 of them, right? If it was the probability that adds up to 7, right, 1, 2, 3, 4, 5, 6. If the question was find the probability it adds up to 5, right? Well, if you were to take a guess, can you see what the pattern is here? What's the probability it adds up to 5? Well, it would be 4 over 90. So if you spot that pattern, right, you can see, well, to get the total number of outcomes, it's 10 by 10 minus 10, right? And the probability of adding up to any number is 1 less that number over 90, okay? Now, interestingly, that happens as well. Just leave that up there. That the same occurs even if it's a massive number, even if it's 300. So the total number of outcomes will be 300 by 300 minus the 300 outcomes where the numbers are the same. So that's the total number of outcomes. And the probability that it adds up to 101, if you could visualize a 2-way table with 300 numbers in it, then the number of outcomes that add up to 101 would be just 100. So it's 100 over 89700, which is the exact same answer that we got in part E. So make of that what you will. It's not worth losing a huge amount of sleep for. Like in most probability questions, there's a specific way of doing it, whether it's Bernoulli trials, whether it's z-scores. This one really requires you to kind of think outside the box to answer this question. Now, I'd say what would have thrown a lot of people off this year was that they probably thought, well, we already use z-scores for part A and B, right? We're hardly asked to use it again. But this is actually a z-scores question as well, or a percentiles question, whatever you want to call it. So you can see that she ran 2 different marathons. These were her positions, right? But you can see the key thing is that there's different amount of people in both, okay? And that she finished 5,265th in this big marathon. But it says her finishing time for both marathons were the same. So we want to figure out what position she finished in this. So it's a very clever question here. And when you learn z-scores from day one, this was what the fundamental use of z-scores is, right? It's a standardizing tool, right? It's a tool for comparing. Like, it would be very difficult to compare these two races because there's a different amount of people in it, right? But by using z-scores, we can merge these down into a z-score, merge this down to a z-score, and that means that standardizes the data so we can compare them much easier. So that's the first thing anyway in this question, is identify it is a z-scores question. So let's have a go off this question anyway. And a good kind of piece of advice for any question like this where it's not immediately obvious how you're going to do it. Even though you might know quite where you're going with this question, we've identified that it's something to do with z-scores. So just start it off. Do what you know is right and see what happens then. And things might come together then if you just tackle it that way. So we know it's something to do with z-scores. We know the process that we take when we're doing z-scores is that we list out the data. So the mean time is 254. The standard deviation for Windy City is 38. But the problem here is that we don't know what her finishing time was. We know her finishing position. We don't know what her finishing time was. And because the times are the same for both marathons, we don't know her time for the Sunny Marathon either. So that's the key to this question. If we can identify what the time is, then we can somehow figure this out. Now, the problem here is, this is a very similar question to part B. Okay, now let's briefly just jump back to part B there for a second. Now, if you think about what we did with part B, we knew that we were looking for the time again. Okay, we had the percentile, so we were working backwards to get the time. So we filled in our z-score, we found our percentile, and we solved the equation then to figure out what the time was. Okay, that's a standard enough type of question. This is the basic type of question where you have the data, z-score, percentile. This is the kind of more advanced question where you have the percentile and you're working backwards. But if you look now at part E again, what you'll notice is that we're actually not given a percentile. Okay, so there's no percentile mentioned in here. So therefore we have to figure out the percentile. Now, what you might spot then is that, okay, so she finished this position out of 6,000. So if we actually just express this as a percentile, that's actually where our percentile comes from, right? Because what this means is that she finished behind 87.75% of the field finished in front of her. So our percentile in this case is 0.8775. And that's the key to this question. We now have our percentile, we have our mean, we have our standard deviation, and we're looking for the time. So it's back to that question we did in part B, or part 2, sorry. So we find our z-score from the log tables. Now the good news here is it's just straight from the log tables here. There's no subtracting it from 1. And now we just put the z-score formula equal to 1.16 and solve for x, right? And it comes out as 298.08, which means that that was her time for the Windy Marathon. So therefore, we now know that that's her time for the Sunny Marathon as well. So we go to the exact same rate, and you'll see now how this all comes together now in a second. So if we do the exact same thing for the Sunny Marathon, except this time we have the time. So if we convert that into a percentile, a z-score first of all, 1.77, then we go to the log tables and convert it to a percentile, we get 0.9616, right, which is 96.16%. And what that translates as is that when Sorka finished this marathon, that 96.16% of the field were ahead of her. Okay, so all we're doing now then is that, well, if there was 2,000 people in the marathon, we just get 96.16% of that, and she finished in 1,923rd, or actually, sorry, there's a typo there, 1,924th position. Okay, so that's how you tackle the question, all right? It's a very similar question to part A, okay? It's just more advanced. Now, the bad news is it's 15 marks for this question, right? So if you didn't make any effort at all at this question, right, or if you didn't even start it, you were in big trouble here, Okay, now the good news is that there was lots of partial credits given out. If you did any of these steps, or if you even got 2 steps right, if you got your z-score, if you got your 1.16, or you were already up to 6 marks. And it was handy enough to pick up marks in this as long as you identified that it was z-scores and you tackled it in some sort of a fashion. You were picking up marks. But if you just left this blank, that's 15 out of 50 marks, which is a significant proportion of this question.